Hey everyone, welcome to the first edition of Astroveo's Coast-to-Coast podcast of science, astronomy, and the world around us. My name is Joseph. This is David, and we're just two friends who happen to be professional astronomers with a deep love of telescopes, astrophysics, and all things science. We've got a great show for you. Today, we'll be talking about a huge plasma burst from the sun that just slammed into Earth a few days ago at 1 million miles an hour, a possible new planet hiding in the far reaches of our solar system, the latest exciting science from the James Webb Space Telescope, and a lot more. So let's dive right in. Dr. David James, coronal mass ejections from the sun. How cool are those?
Very exciting, possibly dangerous, or they do impact humans here on Earth, of course. But
What's
yeah,
life without a little danger?
well, yeah, there's only a certain amount you want, really. But yeah, no. So a coronal mass ejection is this massive outburst of plasma, which is just essentially ionized matter. So we're talking about atoms, molecules that have been stripped of their electrons, and yeah, they've broken free from the sun's magnetic field, and if you're unlucky and they're pointed toward Earth, those charged particles can come your way.
It's my favorite thing about that is that it's like a Russian roulette game
Yeah,
because
that's right.
the whole plasma ball is like polarized with charge, and if the polarization lines up opposite of the Earth's magnetic field, it'll get sucked down the magnetic field lines and cause all the crazy aurora and everything that you'll see. But if
Very
it's
beautiful.
anti-aligned, it'll just get reflected into space and repelled basically. And so whenever you see like it's especially like if you're seeing this huge like chunk of explosion coming at you and it's like there's a 50-50 shot about whether this will be the one. and
Yeah, that's right. Well, it's funny you say that, because that's one of the big problems is you don't see it coming because the it's what we call optically thin. You don't actually see it. You know, you can detect it as it leaves the sun, and as you rightly said, you see the impact on Earth's magnetic field with the aurorae, but you don't. It's in through telescopes. You don't see it coming. So that's the big problem with it, actually.
if we could see it coming, you just know there'd be like sports betting, but for this,
That's right.
with odds updating as it approaches.
That's right. Which continent gets the worst impact, or
Exactly.
who has the nice aurora? The southern hemisphere, the northern hemisphere,
You could do
Finland, Iceland.
combination bets where it's like how far down the latitude goes, plus like how many transformers blow.
Yeah, right. Yeah. How many satellites around the Earth get shorted out, that kind of thing.
Exactly. So, are we seeing more of these than usual? I feel like I've seen more news about this lately.
Well, I think you know this, Joseph. It's near solar max this year, and by solar max we mean the sun is really active. As you know, has a 22-year activity cycle, and we just happen to be right at the top of the activity cycle. So yeah, we should be seeing more of these. It's actually a really natural consequence of that cycle.
It's so fascinating. The sun goes through phases, just like everything else in the universe.
I say everything in the universe has cycles, periods. It's sort of that old adage that everything in the universe rotates unless you stop it doing so. Like, a pencil on a desk is being stopped from rotating, but everything rotates. Everything has a period, and the sun is no different. This 22-year period is based on its magnetic field, of course, but that's ultimately related to the rotation, the internal rotation, the differential rotation inside the sun. Really, really very interesting.
The 22 period is a really critical point there. So a 22-year period basically means it'll go from maximum to maximum again over 20, about 2 decades,
Correct.
right?
That's right. That's right. The half period's 11. That's right.
So that's so funny to me because all the articles that we're talking about the coronal mass ejection that happened a few days ago were saying stuff like it's the largest that has been observed since 2017, and that sounds pretty wild. But if you think about it, 2017 was right around the solar minimum, so it's like saying that the flare that occurred at the solar maximum is the largest it's been since the time the flares weren't so big, and it's like
It's sort
that's
of obvious.
substantially less punchy.
Yeah, that's right. Yeah, no, that's right. It's like this is a really big iceberg because it's bigger than any we've seen since the last big one. Yeah,
Yeah,
it's silly.
exactly.
Yeah, it's a bit sensationalist, which of course a lot of science writing is these days.
Right.
But yeah, no, it's completely natural. It's happened as long as we've been observing these activity cycles on the sun, which really is sort of back to the days of Galileo when he first saw the first sunspots, of course. And sunspots are a natural manifestation of the magnetic field lines threading the surface of the sun. So these things are not sort of new. That hasn't just come around the corner in the last 20 years. We've known about these things for 250 years.
Yeah, Galileo didn't use his telescope to look at the sun, right?
Yeah, well, he must have actually, because it's very hard to have figured out how he would have seen the sunspots otherwise.
Maybe like
Because he,
what about something like what are they called? Like camera obscura or like a pinhole projector or something like that?
Yeah, that's possible. I'm just thinking about that. I'm actually not sure of the history of that, but also one can see the sun. It's very, very low on the horizon, and certainly if it's musk, if there's dust in the air, it's a murky atmosphere. You can see the sun in a really deep orange or really deep red. One could imagine being able to look through it. And don't forget, Galileo's telescope was maybe an inch or two across. The lens was tiny. And don't forget, he ultimately went near blind toward the end of his life. So he did suffer for his observations.
That would explain it, actually.
Oh yeah, he was everything you tell school kids.
That does make sense that, so during the last partial solar eclipse, there was an annular solar eclipse, but in where I'm living, it was a partial one, a pretty large partial one. I was taking pictures, and for the first bit where the sky was clear, I definitely had to use I took Eclipse glasses and I taped them to my phone, and it worked well enough. But as the clouds started rolling in, I noticed that I could just get a picture without needing the Eclipse glasses because the clouds were obscuring it. And I at one point I accidentally, when I was looking up to see where to put my phone, I accidentally glanced at the sun. And even though I looked away immediately, I registered that I saw the partial eclipse with my eye through the clouds, and I just thought that was the coolest thing. It's very unnerving.
It is cool, and I'm so glad you had the experience, but it should be avoided if possible, because as you know, the sun can damage human eyes very easily.
Oh yeah, no, this was super accidental glance.
Yeah,
I not like a point like, look at the solar eclipse.
well, it's one of those things where I've done a lot of work in taking astronomy to school kids across many countries, as it turns out. But it's one of the first things you always say is never ever look at the sun directly, because it doesn't take long to go blind. Actually, it's sort of 8 to 10 seconds and you're in big trouble.
It's a kind of horrifying, actually.
Yeah, well, I mean, it has been done by people in history, and they of course suffered, unfortunately, the consequences of having gone blind. And the human eye is just not well adapted for that level of intensity.
Ironically, though, it's perfectly adapted for the sun, but not staring directly at it.
Yeah, right, not staring at it. Yeah. But it sort of gives you a nice contrast for astronomical objects, because of course you can stare at the full moon and your eyes aren't damaged. So it gives you a sense of how very much brighter the sun must be that our eyes can do that.
So that's right? You can stare at the full moon and your eyes won't be damaged. But to be honest, when I'm looking at the moon through my telescope, I feel like my retinas have been nuked, and it just torpedoes my night vision.
Yeah, of course, completely. Yeah. Well, don't forget to tell your. I can't remember how large is your telescope? Is it 8 inches diameter?
It's a 6-inch, yeah.
A 6-inch diameter. So that's collecting an awful lot of light, right? I mean, I can't remember what the average human pupil is, but that's.
I know this one. It's like
8 millimeters, is it?
It's like a order of like a centimeter to a centimeter and a half, I think, when fully open.
A center. So that means your telescope is 15 times the diameter of a human eye. So you're collecting an awful lot of flux. You're collecting 15 times more photons. So your poor eye is probably thinking, "Don't show me the full moon."
That makes complete sense. So circling back to the sun bit. So I did a little bit of research, and because I found the comparison to the solar minimum absurd. I did a little bit of research, and it is the largest solar flare since the last largest solar flare during this last solar maximum, about 2003, which lines up with that 22-year cycle. And so that was an X-class flare, an X45 class flare, and it was actually the most powerful solar flare ever measured. And I thought that was really interesting because I've heard of more damaging solar flares throughout that have been recorded. Like there was one in the late 1800s that I don't know if they knew it was a solar flare at the time, but I think they recorded extra large sunspots, and then a couple days later all the telegraphs in the world were like broken and like there was like the capacitance of the air had like quadrupled or something like that. But I think we have an estimate of that one. So do you think that this was a very powerful solar flare, but maybe wasn't aligned with the Earth's poles, and that's why we didn't see as much of an effect back in 2003? Or
Yeah, that's possible, of course, or it could just not have been directly pointed at the Earth. We could have been sideswiped, where maybe the one that you're referring to in the 18th century or 19th century was directly pointed at us. And so
That's a
maybe
really, really good point.
yeah, so I mean, I think that's a really big misconception is if you have the sun here and you have these enormous explosions of material in these coronal mass ejections, if the Earth is sort of in its orbit, sort of roughly over here, the beam of particles could actually, of the solar wind, could actually pass sort of underneath, quote unquote, the Earth and not impact us at all. So it depends where where the solar flare is, it's sort of exploding toward. Like if the vector's not co-aligned with the Earth's orbit, and don't forget the timing has to be right, because of course, let's say you know, the Earth as it's orbiting is sort of doing this. If the timing isn't right, it can either pass behind or in front of the Earth's orbit, so you're not directly impacted either. So the direction and the timing has to be right for us to be fully impacted.
That's really fascinating. So, like, will the sun get better with practice?
It's a terrible joke. That was pretty good. That was pretty good. There you go. That was good. I like that. Yeah. I mean, you have to remember, though, don't forget, though, the sun is really old. It's 4.5 billion years old. If you compare it to really young stars, let's say the stars in the Pleiades, the Seven Sisters, for instance, those are 120 million years old. Those are really active, and that's because they're spinning really, really quickly, which winds up the magnetic field. So those types of stars, these very, very young stars, they have very, very much more active flares. And so if we were orbiting one of those types of stars, a very young star, at the same distance we are right now from our sun, we'd be in big, big trouble. We'd be blasted by X-rays and UV and particles and so on. And I don't think our magnetic field or our ozone layer would be able to protect us, actually.
Interesting. That's really, really interesting. So is it the orbit, or is it also something to do with the sun's like level of activity?
Yeah, the sun is really very, very inactive. I think at any given time, even during solar maximum, the sun's surface is covered by about 0.5% by area with these sunspots, which are magnetic fields sort of poking through the surface. So that's at the maximum 0.5%. So even though you see sunspot groups and you think, oh, that's amazing, that's super cool, look at how active the sun is, as a fraction of the total surface area of the sun, it's really a very, very small amount. In these super young stars I was talking about, you can get sunspot filling factors or star spot filling factors of about 30–40%.
Wow.
So that's enormous. Their magnetic field is very, very much more active. It's incredible.
That's so cool. 40%. So that's like half of a sunspot, basically.
That's like half the surface, yeah. And if you go down to some of these M stars, these M-class stars, our sun's a G-type star. These M-class stars, which are very, very low mass stars, some of their surfaces can be near 100% star spots.
Oh my God.
It's incredible. Yeah, so they're just incredibly magnetically active.
So, this is more personally related to like a personal interest for me because it's related to my research. But with these stars, where you have like 50% of their surface, being sunspots, does that affect stuff like the stellar wind? Like so for viewers that don't know, the stellar wind is basically as a result of a star's magnetic field carrying charged particles away from the star and depositing it into the area around the star. So if the sunspots are some level correlated with the star's magnetic field, if you have these stars that have a very big sunspot filling fraction, does that mean you'll have like one side of the star that has a weak stellar wind versus the other?
Well, so that's a really interesting question, and it's not quite as simple to answer as you think, actually. So don't forget, a stellar wind, or for us, a solar wind, those particles have to be, they emanate from open field lines, magnetic field lines, which means if you think of the star as an orange on my hand, right, the field lines have to be open so the particles can flow along them. When a star is very, very magnetically active, what you actually get is these loops, these magnetic loops that are called arcades. And unless there's a coronal mass ejection where the magnetic field blows open, the particles actually do not escape. So the solar wind or stellar wind is a very sensitive function of whether you get coronal mass ejections or not. If you don't, the wind doesn't increase that much because the particles cannot escape the magnetic field lines.
That's incredibly interesting.
Yeah. So for instance, in our sun, where let's say, again, my fist is the sun, let's do it that way. If this is the North Pole and this is the South Pole, The field lines, well, I can't really do it easily here, but the field lines are really, really big and open like this. But what happens is if you've got these open field lines, the particles can escape. So the greatest part of the solar wind actually escapes through the magnetic poles because it can go along these open field lines off into solar system space.
That's so cool.
Yeah, so your question was a really good one, but not that easy to answer, actually. There's some complexities in there.
It always ends up that way.
Yeah, of course. Stars are complex beasts after all.
I have a 40-page book by Chandra Sekhar that suggests otherwise.
Well, unfortunately, or at least unfortunately for me and you, he was a genius, right? So he knew stars inside out.
So before we move on to the next topic, actually I can pull up a cool picture of the flare that hit that eventually hit the Earth. So this is a picture from the NOAA Space Weather Prediction Center, which in my opinion is like one of the coolest websites on the internet, where you can just watch the sun live and they're like, oh, some space weather coming up. So this is a picture of the sun. It's at 131 angstroms. I've always wondered this. This is the filter they pick. Is the flare just not visible in all filters? It's such a big event. You'd think it'd be visible in all filters, but like.
So that's a really good question. I think the answer is, if your eyes could do it, then yes. We don't have good enough observatory spacecraft to observe it in all filters. Now we can observe it in the wavelength that our eyes can see, human eyes can see, but 131 angstroms is sort of extreme ultraviolet, or just bordering on what we call soft X-rays, very low energy X-rays. And don't forget, our eyes can't see in that domain, which is why we need the spacecraft. Right. So this is a very interesting one. This does look like a flare, a flare event, which is this really big release of energy. If it's in extreme ultraviolet or soft X-rays, that is definitely accompanying a large magnetic field, and the plasma gets accelerated along the magnetic field lines and releases all this energy. But if we were looking at the sun at that point, if our eyes could see something so bright, I'm not sure what we would see. We may be able to see something, because what ends up happening is if you've got a magnetic field line like this on the surface of the sun, and the plasma ends up going along the field line and being accelerated and releasing this, extreme ultraviolet and soft X-rays, you do end up seeing it, but you're not seeing it itself. You're seeing scattered sunlight from the surface of the sun off the plasma into our eyes. So you might be able to see it in the optical, which is where our eyes see, of course, but you're not seeing it directly. You're seeing scattered light from the surface of the sun.
Okay, that's a really important subtlety, which I feel like is often glossed over in discussions of this.
Yeah, that's right. It is very, very subtle. People think you're seeing the direct optical light from the flare. But typically, if you're seeing a flare, you get radio emission, because, of course, the electrons are spinning around a magnetic field. So you get lots and lots of synchrotron radiation. And then you get they're being massively accelerated, because these magnetic fields are enormously strong. So what they do is they accelerate the particles, and of course, accelerating charge in the magnetic field releases energy. So you get this massive release of high energy, extreme ultraviolet X-rays and so on. But the visible light that you tend to see from flares is reflected sunlight. And you can tell this because when you look with a special instrument called a polarimeter, the light is polarized, which means it's being scattered. And that's how we can tell.
That's so cool.
Yeah, it's amazing.
I
apologize. Yeah, if you're interested in why I seem to be really into this, is my PhD was actually in this type of science, and so the things you're describing was exactly what I used to do in the mid-90s.
So count yourself lucky, guys. David is literally one of very few world experts on this stuff.
Yeah, well, I moved away from it a little bit, but I still remember all this stuff from my thesis, and of course, I was referring to the Pleiades, these very young group of stars. They're a big milestone for stellar evolution, as in working out what happens to stars as they age. That was sort of my bread and butter for 20 odd years, and it was wonderfully exciting to be doing.
All the stuff related to the Pleiades, first of all, awesome astrophotography target.
Oh yeah,
definitely beautiful. Do a video on it in the future. Gorgeous.
Well, so that's part of the reason. In fact, funny you should say that. And I've seen your pictures of the Pleiades, just beautiful. is that most of the stars you see, the bright ones, are all blue. And that is because you're picking up the very hottest or among the hottest stars. And so their surface temperatures are way above 10,000 degrees. And so they come out blue when you take photographs of them.
Is it a selection bias? Because I know the Pleiades in particular, they're surrounded by I can't remember what it's called. It's like the gas, and there's like a interconnected nebula or something.
Well, Interstellar Nebula. It's actually
Yeah.
a bit of a myth that, in fact, people think it's the gas that's left over. I know what you mean. There's like this blue wispy cloud. It's a reflection nebula. Yeah, that reflection nebula, a lot of people think it's the leftover gas from the formation of all the stars in that cluster. It actually is not. It turns out it's a nebula of gas that's actually in the middle of, if this is the Pleiades, and there's a couple of thousand stars there in total, actually, this cloud is passing right through them. So it's not a leftover from their formation. It's just an interstellar nebula that's moving through them.
Oh,
and
wow.
And it's a reflection nebula. So it comes off as this sort of blue haze as it reflects all that blue light from these very hot stars.
That's
beautiful.
So cool.
Yeah, very beautiful. It's actually a pain to deal with when you're looking at those stars to measure their photometry, the light that comes from them, to measure their age and their surface temperature and how far away they are. It's actually, you have to deal with that contamination. It's actually a contaminant.
That is, I feel like so much of astronomy is dealing with those kinds of contaminants and applying corrections. Dust, interstellar scattering, like redshift effects.
Redshift effects, all that, yeah.
Okay.
Look, so actually, on that exact point, open clusters, which is what the Pleiades is, very funny objects that when you measure them and you point a telescope toward them, of course, if you're lucky, there's 2,000 or so members, 3,000 members. The Pleiades is pretty rich. But what you, of course, when you measure an image of that part of space, you, of course, measure all the stars around it, the stars in front of the object, of the cluster, and the stars behind it. So you may measure a couple of 100,000 or maybe 1 million stars in your image, but only a couple of thousand belong to that cluster. And so an awful lot of the work is actually eliminating those contaminants, those sort of interstellar interlopers that are non-members of the cluster.
And do you do that by like proper motion analyses or something?
That's yeah. So you can do it in a couple of ways. You can do it with proper motions, which is the sort of the relative two-dimensional motion across the sky. So, for instance, the Pleiades might be doing this across the sky, but the other stars will have a different motion depending on their position in the galaxy. You can measure what's called their radial velocity, which is their line of sight velocity. So a group of stars that are all born from the same cloud all have the same radial velocity. So the Pleiades radial velocity, I can't remember its absolute number now, it's 20 kilometers a second, I think, something like that. All those stars in the Pleiades are moving through space with the same radial velocity. And so what you can do is you can measure the radial velocity of all the stars in the image and eliminate the ones that are not that don't have the same radial velocity, that don't have the same proper motions. And in this day and age, of course, because of things like Hipparcos and Gaia satellites, we can measure their parallaxes, their distances. So you can eliminate those stars that don't lie at the same distance.
Oh, wow. I can't imagine. I can imagine, like, especially with Gaia and how intense its survey has been. We've probably discovered we've probably much improved our understanding of these kinds of objects.
Oh, huge. It's been a game breaker. It's one of the most wonderful satellites we've ever put up there.
I actually, there's I went to a talk LC over recently on Gaia, and it was like an instrumentation talk partially, and so we got to see the how the CCD worked, and it's like so cool.
Oh, it's amazing.
Amazing instrument. Amazing.
Yeah,
instrument.
Well, one of the big problems is actually the sheer volume of data that it releases that's generated.
Oh, yeah.
Because of course it takes images fairly often because it's got this huge orbit, and so it takes images all the way along to work out the geometry to all the stars and sort of triangulates essentially, which is more or less what parallax is. And so it's the quantity of data is just staggering.
I mean, literally billions of stars.
billions, well, hundreds of billions at this point, I suspect.
Oh, right. Yeah. I mean, billions within like the first year or so, and now they're way down the line.
Yeah. Well, don't forget, you can't see past, you can't see through the galactic center, for instance. So if there are 400 billion stars in the galaxy, there's a couple of maybe 100 billion per section, per quadrant you can look at. You can't see behind the center of the galaxy because it's all, just line of sight difficulties with dust and there's other objects in the way. But yeah, you can certainly see all the local group of stars, and then the ones off to the side of the galactic center. So yeah, we're probably at well over 100 billion stars have come out of that survey. Amazing.
Remarkable.
Yeah.
Okay, so our next topic up, really cool paper popped up on Archive this week, a new ultra short period binary discovered. So for those that don't know, binary star system, most stars in the sky actually that you see are part of binaries. Basically, it's not just a single star like the sun, but two stars that are orbiting each other. They can be the same type, different types. And so that's extremely, extremely common. And so some of the most famous stars in the night sky that you'll know of actually are binaries. Like the best one I can think of, the brightest star in the night sky, Sirius, is two stars. Sirius B, I think, is the bright one, and then there's a very small one that's right next to it.
It's the other way around. Sirius A is the A0. I think it's A0 star, and Sirius B is a white dwarf.
Yeah, sorry, other way around. Yep, you're totally right. Yep. And so basically how fast they orbit each other is of great interest. And it's been theoretically predicted that you can get some really low periods depending on how the binary was produced, basically, and what type of stars you have. And so there's been a new discovery of an ellipsoidal binary with a 20-minute period. So that means two stars, not necessarily like the sun, but like much bigger than the Earth. Actually, one of them is a white dwarf, so not that much bigger than the Earth. But two, stars are orbiting around each other in under 20 minutes, which is just completely bananas.
It's incredible. What is the primary star, the bright one? Do you know what spectral type it is?
Let's see. So the visible star. The visible star is being. So the companion is a carbon oxygen white dwarf. It's invisible. The primary star is an AMCVN star.
AMCVN.
Yeah.
So AN is typically an A star that's magnetic. CVN. Yeah.
CVN is a Canum Venaticorum.
Yeah, that's right.
It's a cataclysmic variable.
Those cataclysmic variable as well. Yeah, well, that's interesting. So if it is an A star, that the white dwarf must have been evolved. It must have evolved, right? Because stars are not born as white dwarfs. So it's the leftover remnant of a higher mass star. So that probably means it could be a very high A star or a B star, which means it's the system itself could probably only be 100, 150 million years old, possibly less. So it's a very young system. Yes, very young. And 20 minutes, I mean, again, most stars aren't born in such short periods. What ends up happening is they're formed at some distance, and their orbital period might be, who knows, a couple of days, maybe. A couple of days is still a short period, but they must have come together in orbital period over the lifetime of the binary, which.
So actually, this is an area that I know a bit about. So a fun fact, because a lot of people binaries are quite common, but binaries actually cannot form by themselves. So what I'm guessing happened with this one is you had a third star that got ejected, releasing the kinetic energy, which allowed the two stars to increase their potential energy, basically, to compensate. So they may not have drifted together. They may have just basically collapsed together after a third star was ejected.
Yeah, that's very, very common. But what you can get is you can get what's called spin orbit coupling. And so essentially the spin of the stars themselves can couple gravitationally with the orbital period. And what they can do is they can actually interchange angular momentum. So the spin of the stars can borrow, quote unquote, angular momentum from the orbit of the stars. So the orbit shrinks, but the stars themselves spin up.
Whoa.
And so they could be rapidly rotating as their orbit is shrinking.
That's so cool.
Yeah. And don't forget, they're also, if it's an elliptical orbit, if it's circular, it happens, but it's harder to do, of course. But if it's elliptical, like an egg shape, if I do it this way, that means there must be periods in their orbit where they're actually quite close together and then farther away and then close together and then farther away. So as they come closer together, they can have this spin orbital coupling where they interchange angular momentum. So their period can get shorter and shorter.
Is the spin orbit coupling mechanism, is that like a tidal disruption?
Yeah, essentially, yep.
Okay.
Yep.
That's so it would make sense that it's being magnified as they get very close together.
Oh yeah, no, absolutely. Of course, because of course, gravity, as you know, gravity is a sort of 1/distance squared effect. So in fact, as the closer they get, the stronger that coupling becomes.
That is super cool. I love this binary star stuff, and the systems are always so extreme. Like this star in particular, the White Dwarf Companion, it's about the mass of the sun, but it's 10 times smaller, and it has a surface temperature of 25,000 Kelvin, which is
Wow.
like absurd. I mean,
yeah, so that's very hot. So that also suggests it's young, by the way, because obviously white dwarfs will cool, they'll radiatively cool as they age. So 25,000 Kelvin is quite hot. So I suspect this is of the order of 100 million years or less.
So if it's over 100 million years, then is it possible that we could spot the sacrificial the third star if on its way out? It can't have gone that far.
Yeah, that's a good point. That is a good point. It depends on the ejector, on the ejection speed of the tertiary component, because it could have gone, and we don't know the direction in which it's gone off. But there could be a very high proper motion star in the vicinity, which would be a good candidate for that third party star, taking away all the angular momentum with it.
That's a really that would be really exciting if we found the star that pushed those two together.
Yeah, that's a good one. I suspect the authors have looked for that star, but if they haven't, it might be worth dropping them an email and saying, "Hey, have you thought of this?"
That's a great idea. I didn't even look to see if the authors were anyone we knew. I think it's I think it's I don't, but it's a team from Beijing. So I don't know any of them personally, although I do have some collaborators. Oh wait, oh my God, it might be a different Wenchang, but I do have a collaborator who does this and he does supernova remnant stuff too. There's maybe somebody in the global supernova project on this paper that
that's interesting.
Might be able to reach out to him.
Yeah, maybe make that suggestion. Yeah. Look for high proper motion object relatively nearby. Do you know how far away is the system?
Oh, that's a great question. I don't off the top of my head. Here. Why don't I share the paper and we can take a look real quick?
Yeah, throw the paper. Maybe give me the star name. I can do a quick search.
Okay. Oh, this is a big one. So this guy, Wenchang, he is oh, and he's at Tel Aviv. I think this is the Wong Lee that I know. So that's super cool. We could reach out to him. I've emailed with him in the past.
What's the system name?
The system name, it's a long one. TMTS J052610. This whole beauty.
Yeah. All right. Well, after we finish, I'll actually have a look at this.
Sure. It's on my blog, and if you guys want to, if anyone's watching, you want to read it too, it's just jrfarrow.blog. The paper is linked there.
So maybe the question to ask, and maybe our viewers would think of this too, is who cares? Why would anybody want to study this kind of object?
Yep. It looks like it's 8 kiloparsecs, by the way, from the galactic center.
8 kiloparsecs
from the galactic center.
Oh, I see. So is it relative to us? All right. Well, I'll figure out the distance.
So why is it important?
I think we are also 8 kiloparsecs from the galactic center.
So it's right at our orbit.
Yeah, it's actually. Oh, it's the moon. Interesting. So yeah, the question to really ask is why do astronomers, professional astronomers like us, why do we care about studying these kinds of objects?
That's a really good question. I think you'd actually have better insight into that than I would, since your stuff was more your research has been very related to this. You can definitely give a better answer than me on this one.
Yeah, I mean, I think we're good friends, you and I, but I wasn't trying to put you on the spot. I think it's
no, not at all.
It's one of those things where I think I would want to know the answer to this. And I think there are two biggies. The first is it's clearly related to stellar evolution, because the white dwarf must have undergone some cataclysmic process, probably a supernova-like event, or at least a series of novae events. And so that in itself is interesting, with the fact that the AM star has survived, because one could argue it could have been either sort of disrupted in the orbit, or it could have absorbed an awful lot of the ejecta from the white dwarf's progenitor, the host star. And the other is just to try and understand orbital dynamics. And that's important for all kinds of reasons, because understanding how stars form, understanding how stars orbit each other gravitationally, has all kinds of implications for even our own sun, because we have an effect on the sun, the Earth does. But of course, Jupiter and Saturn are the two biggies in the solar system. While all the orbiting planets are dominated by the sun's gravitational field, we also cause the sun to wobble slightly in its orbit. And so understanding orbital dynamics of systems with very, very different masses and or evolutionary status is actually really interesting from an astrophysics point of view, but it may help us understand our own solar system as well.
So is it our solar system it has a single star, whereas this is a binary. Is it possible our solar system had a binary companion in the past, or will capture one in the future?
So that is a really interesting question. That's a hard question to answer. The very fact we have a very stable solar system with most of the planets being coplanar, they're all on the same ecliptic plane, and relatively stable in their orbits, would suggest that probably there wasn't a binary companion. There doesn't seem to be any star in the that we can find that looks, so we're not in a very wide binary. So, if the sun's here and all the planets are here, there's some other star that is a member of the solar system, but way, way, way far away. We can't find any evidence of that, at least not substantial evidence. Could it do so in the future? I suppose the answer is yes. We could gravitationally come very close to another star system and capture that system. Or if it's a high mass star, we ourselves could be captured. And by captured, I mean gravitationally attracted to that star.
Well, we wouldn't be able to capture it outright. We'd have to run into two other stars first.
That's
right?
probably true, or unless there was maybe like a giant molecular cloud like the Orion Nebula next door that could act as a mass proxy. But you're right. I think the idea you're getting at is the fact that if we're crossing each other, the sun and another star in space, even at relatively low velocities, we're probably going to go right past each other. Even though we may slow each other down, we're probably not going to have it. There's too much motion in the orbital motion in us and the captured star for us actually to capture each other. So I think you're right.
I don't think it's possible. Like in terms of the n-body problem, I don't think it's possible for two bodies to start separate and then drop into a stable orbit, orbiting each other stably.
Yeah, it's at least highly improbable. But you're right. You need a third party, and that could be another star or a star cluster or a giant molecular cloud, something that has substantial mass to help you drain some of that gravitational kinetic energy away. Yeah, that's a good observation.
I love seeing studies like this. They've got beautiful spectra. Oh my goodness.
Oh, that's beautiful. Yeah, you see all those deep valleys. They're all hydrogen absorption lines.
Wow. How come we don't see a ton of emission here?
Because these types of stars, although the AM suggests that there is some magnetic activity, but it's very low. Higher mass stars. Is this just the? Let me look at the temperatures. Hang on. Temperature. Oh, this is of the white dwarf, actually. See here it says 25,000 Kelvin. That's actually the white dwarf. Yeah, the Balmer series lines. So white dwarfs, while they themselves have magnetic fields, very strong magnetic fields sometimes, they don't have much of an atmosphere to actually produce these emission lines. And the AM star doesn't have much of a magnetic field either. And so emission lines are typically caused by very intense magnetic fields exciting the electrons in the outer atmospheres of these objects. So you typically don't see emission lines for these types of systems.
That's really interesting. And I'm used to supernova stuff where we get a ton of emission because you basically have like a glowing, expanding shell. It's so cool to see the spectra for other objects like this.
Yeah,
this is a good paper.
Is it? Yeah, just show me that again. Is this a real spectrum? Oh, it is. I think it is.
This is the blue solid lines are the model fit.
Ah, yes, indeed. So you see the Balmer series. These are hydrogen hydrogen absorption lines. It's interesting though.
Do you remember which transition the Balmer series is? Is it
I was
Three to
just thinking the exact same
four.
thing. I think it's is it 3-2 or 4-3? So
Let's
you've got
find out. Ballers.
Lyman. I think it's 4-3.
It's a 3-2.
Oh, three to
I
two.
think
Okay, next one down.
3-2
So
for
so
for
four
hydrogen alpha.
yeah, for hydrogen. Oh, yeah. Well, hydrogen alpha is
Yeah.
Lyman. That's right. That's
Yeah.
2-1. And what we're talking about here is if you have an atom and you have electrons orbiting it, say hydrogen, for instance, the very, very lowest orbital of electrons is called level 1. If it gets excited into the next level, that's called level 2. And so when that electron de-excites, it goes from 3 to 2. That would then emit what we call Lyman alpha, which is the first excited state of hydrogen. So Balmer is the next one down, and that is from 3 to 2. So if this is your hydrogen atom, there's the first orbital, there's the second, there's the third. It's an electron being excited from 2 into 3, and then when it de-excites, it releases energy, and that would be hydrogen alpha, which is this very far right absorption dip here. Yes, that one, and it's at 62.8 angstroms.
And then these are as you get the higher level transitions, right? 3 to
Correct,
2 and
correct.
then 4 to 3. Yeah.
No. So 3 to 2,
3
4
to
to
2 is this
2,
one. 4
5
to
to
2.
2.
Yeah.
The first,
Yeah.
3 to 2, 4 to 2, 5 to 2, and so on,
Right.
all the way down to the break. Yeah. You're right. Very beautiful spectrum, and you can
Yeah.
see how it's
So
peaking.
cool.
It's peaking way down here in the blue, which suggests its temperature is very high. Which this model is 25,480 Kelvin. So very nice spectrum.
It's such a clear black body too, which is super nice.
Yeah, that's right.
Okay,
Yeah.
I'm gonna stop sharing. All right. So next topic.
Mm.
A possible hidden planet in the Kuiper Belt.
Ooh.
Yes, this is an exciting one.
Why only possible?
So this was done via simulation. So they didn't discover like a
Ah,
potential, or it wasn't like the case with Uranus where we discovered Neptune because we saw that Uranus's orbit was being perturbed. So as you know, you may or may not know, solar systems can capture other planets. So there are plenty of planets just marching around the galaxy. They're called rogue planets that they don't have a host star. And if they go
free floating.
free floating, right? Most recent discovery actually was like the JWST with the jumbos, the Jupiter mass binary objects, which are just so creepy and so cool. So solar systems can just capture free floating planets around. The question is that the study sought to answer was basically what's the likelihood that we captured one in the past, and that if there's one out there. And so they did this very interesting analysis. They basically created a simulation based on something called a mass function, which tells you basically how much free floating planet mass you're going to expect to pick up based on assumptions in other physics. It's something that's quite challenging to measure, but you can measure it via both theory and experiment by looking at other solar systems and stuff. And like what planets they've captured, if you can tell that. They've created the simulations and checked of our solar system's evolution and checked to see how many planets we captured in the simulation and how far out they were. And they found that we captured a little over one free floating planet on average with a mass greater than Mars at a median predicted distance of 1400 AU, which is 1400 times farther than the distance between the Earth and the Sun. And so on the face, that's pretty cool. The face value, like interpretation, is there's a pretty good likelihood that there's a hidden planet with the mass of Mars out there in the Kuiper Belt. And so that by itself is pretty exciting.
Right. This is all theoretical, but that's the prediction they're making.
It's all theoretical, right?
Yeah. So these predictions can be really sensitive to the input parameters that you use. And so it'd be interesting to see if the input parameter was off by 20%, for instance, would you still have that one potential free floating captured planet?
Yeah. So it was a fun study to read, but this is my biggest confusion with it. So I can share my screen and show some notes on this. So basically, the mass function that they use is right here, and it has this. It's pretty dominated by this coefficient, this 2.18 plus or minus 1.4, and basically, if you change the value, this value 2.18 within the reasonable error bars, you'll get quite different answers. And that's totally fine, right? That's how science works. We do things with uncertainties. The problem was the paper didn't report how the resulting uncertainty on the captured free floating planet estimate. So if these error bars are really tight and you have a really good understanding of your mass function, then you might have low error bars. Like you might get like 1.2 plus or minus 0.1 planets. And so that tells you, okay, this is a really robust analysis, and you're likely to have this is likely to reflect reality, at least if the assumptions hold. But the problem is these error bars are so huge, and the error bars on this alpha parameter are comparably large. It's my initial, just some back of the envelope math will tell you that if you vary these coefficients, you'll end up with quite a different value.
Yeah,
and so it's
right.
very important to see what the error bars on that number are to assess how important this is. But the paper didn't include it, which I thought was a small, it could have represented a good improvement to the analysis to include that.
It was an oversight, maybe.
Mm-hmm. It was not just limited to that too. Also, in their simulation parameters, like the choice of binning, which is just a setting that you determine in the simulation. It can't really be determined by theory. It's how discrete your problem is, basically. Their estimate changed by a factor of 3. And so if they went from 1 to 3 captured planets with one particular change of binning, but given how sensitive their estimate appeared to be, I would have liked to see a wide variety of bins checked and compared to the resulting value. Because if you go the other way and it goes from 1.2 to 0.3 or 0.4 planets captured, then it's like the conclusion of the study might have been totally different. It might have been, it's very unlikely that we captured one, instead of what it was, which was pushed in the media there's likely to be a planet out there. Because there's quite a lot of media discussion about this, and so I think it was a very, very interesting analysis, and I think there's absolutely a room to continue investigation.
As is the nature of most science.
Have you seen the JWST picture of Jupiter mass binary objects, which are a class object related to this stuff?
I have, but you feel free to refresh my memory.
So I just found them so cool and so weird because they're so literally in the Orion Nebula. JWST identified these objects that are literally pairs of planets just floating around.
Yeah.
And it's like you can very clearly see that there's these distinct planets, and I find it the craziest thing ever. That we can even have achieved resolution to see pairs of planets in other, just so far away from Earth. I mean, the Orion Nebula is 1,500 light years away.
That's incredible. So just to be clear, if you zoom in a wee bit and then follow follow them. The actual pairs of planets is these two, where you have control of the screen, but it's those two dots above it. That's right. There they are.
Yeah. And so you can see the zoom ins here. These are distinct pairs, and it's they're just so close to each other. I mean, obviously, talking cosmic distances, but they're just so common and relatively close in the nebula. It's how do these form? Are they do they just form in free space from the gas floating around in the nebula? Do they form in a solar system and then get ejected?
Are they failed stars?
Right.
I can't remember the actual mass of these. I'm not sure the mass has yet been measured, but they could be essentially pairs or binaries of brown dwarfs, which are failed stars. So
also, I think failed stars is a little chart. Why don't we call them pre-success?
Pre-success stars. Yeah. Now, these brown dwarfs typically tend to be lower than 8% of the sun's mass. And downward, of course. So these are, I think they have to be 80 Jupiter masses and above to be called a brown dwarf. So I don't actually know the mass of these, but
in the name, they're Jupiter mass binary objects, so they're comparable to Jupiter's mass.
Yeah, but they could be 5, 6, 8, or 10. I haven't seen the study. I suspect.
I know what you mean. It's those ads where it's we deliver it to your home in minutes, and then it's 500 minutes later.
That's right. That's right. That's right. You get your pizza in 25 minutes or less. Or how many integrals of 25 do you need? But yeah, but still phenomenal to find them what is essentially free floating, very low mass objects. But of course, they could, as you say, they are pre-success or failed stars. Or they could be ejecta from third body or multi-body interactions. Don't forget, we haven't seen these previously because this is an image that was taken in the far infrared or medium infrared at least. And so we're able to peer through the very extensive gas and dust cloud that is the Orion Nebula, stellar nursery, if you will.
Not to mention, I mean, these are very on the edge of JWST's resolution, and it's already enormous and bigger than anything we've had before. So,
it's incredible, yeah. And you can see actually in the top left of the image, this white horizontal bar is representing the scale, and it says 1170 AU, and we rightly said 1 astronomical unit is the mean distance between the Earth and the Sun. So this is something like 10, 20, nearly 30 times, this white line is 30 times the orbit of Pluto and the Sun, approximately. So these distances between these two objects here, for instance, this one here that's at the sort of 10:30, 11 o'clock position, is just enormous.
Well, it doesn't seem that. Yeah, I think it's actually the opposite.
Well, it must be 10 AU.
That you mean between the two?
Yeah. So
sorry.
10 AU is like the distance, say, from Saturn to the Sun.
Sorry, I thought you meant the distance between like the two objects, the parent distance there. No, yeah, that's that's quite large.
Yeah, that's incredible.
It's quite substantial. But the distance, I mean, this is like probably roughly 2000 AU, which is like, I mean, if you started at the Sun, 2000 AU is like you'd be out at the outermost edge of like the Oort cloud, right? At 2000 AU. You wouldn't be quite to the next star, but you'd be at the farthest edge of the solar system.
Yeah. No, you definitely nowhere near the next star, but it's
like having these pairs like within basically a solar system distance of each other is kind of freaky.
Well, you've got to be really careful here because this is a 2D image.
Right,
one could be in the foreground, one could be in the background. Yeah, the distance could actually be way farther.
It does look. I think I'm getting tricked because they look so comparable in size. Like my mind is like, oh, they're at the same.
Same. You actually don't know the orbital projection either. So it's. I mean, yeah, we have no sense of how close, unless they have. Well, they can't have parallaxes. So yeah, we actually don't know the distance between the groups there.
I hope JWST makes a time lapse of one of these or something, because that would be so cool.
That would be cool.
Although if they're at a distance of like Saturn, though, they'll probably make one orbit in like 30 years, like Saturn does, right? So
yes, that's right. And again, that's assuming if you're seeing them plane on, if they are perfectly circular, not orbital, elliptical. Although I shouldn't actually change the period, but still. But amazing.
It's remarkable. Absolutely remarkable.
Oh, there you go. Actually, if you have a look down there, they have mass estimates. They have mass estimates.
So then you're right, like 3 to 7 Jupiter masses.
Yeah, like. that sounds about right. So they are they're sort of they're right on the edge of being brown dwarfs. So they're super Jupiters or very low mass brown dwarfs.
They're steroid Jupiters.
This is a really good point for our viewers, however. So when you see something like this on an astronomical image that says 4 Jupiter masses or 3 Jupiter masses, almost always those are estimates or they're based on some theoretical stellar model. So we don't actually know the masses of them. They just appear to have the right brightness and color temperature to be the mass that we're talking about. But these masses could easily be a factor of 2 in error.
Since these are like Jupiter mass objects, relatively speaking. Sorry, Astro Puppy wants to join the conversation. You'll come here, pal. Since these are he's tired after a long day of filming reels with no pay.
Another feeling.
Sorry. Yeah, so factor 2. I'm wondering if these are planet-like objects. Like, even if they're brown dwarfs, is there a brown dwarf like mass lumin? Because they're not glowing, right? We couldn't use a mass luminosity relation for it or anything. right?
No, well, you definitely couldn't do the luminosity unless you assume the mean distance to the Orion Nebula. But
Right.
no, these are actually they're just
But
stellar
what
models.
I mean is they're not nuclear fusing, so it's not like we
No,
can.
no,
Yeah,
that's right.
they're entirely being illuminated by reflected light from like the nearby stars.
No, that's not necessarily true. In the infrared, they are emitting because they're undergoing gravitational contraction.
Oh, right.
Just like Saturn and Jupiter, while most of the light we see is reflected sunlight, they themselves emit infrared light into space because of the internal energy due to contraction.
Right. I mean, effectively, we know that like even like the Earth has a hot core and stuff that's going to be emitting some level of thermal infrared.
That's yeah, it's probably very low. Don't forget by the time that hot core energy gets to the surface, it's so distributed. I mean, I don't know what the average surface temperature of the mantle is, but it's very low compared to the several thousand-degree core. But these are emitting their own infrared because they're undergoing gravitational contraction.
So
So
like they're collapsing and it's being converted to heat. The
yeah,
energy.
just through friction essentially, or conservation of energy as it collapses. But the I mean, you can already tell in these images the next nearest star for some of these pairs is thousands of astronomical units away. There's no way
Yeah.
their cloud decks could be illuminated by those stars that we would see them.
Okay.
So
Gotcha.
it's actually internal energy due to their contraction.
Okay.
I
That's
mean,
really
don't forget
interesting.
the Orion Nebula, by the way, is about 1-2 million years old, perhaps. So these are very, very young stars or
Okay.
objects, and so even the star-like systems in this object, this nebula, they're not fully turned on stars yet because they're too young.
Okay. That makes sense, and it's kind of making me want to get an IR filter for the 6SE.
Well, if you do get your IR filter, you'll probably just pick up the irradiation or the emission of the filter itself.
Really?
Yeah, because don't forget your filter will be at whatever observing conditions you are. Let's say even if it's 50 Fahrenheit, that's blazing away in the infrared.
Okay.
And also, you don't have a detector to detect the infrared.
Oh, well, I mean, my CCD is sensitive to infrared, actually quite sensitive. I have a ZWO ASI 224MC.
How far out does it go? What's the transmission curve?
Oh, that's a
Or,
good question. I don't know off the top of my head.
yeah. I mean, even if it goes out to 10,000 Kelvin, which is the very, very near infrared, that's the sort of the best you could hope for. And don't forget, the night sky especially is blazing away in the infrared because of all those water molecules vibrating.
Yep. Okay. So
Yep.
Ixnay on the IR filter.
Yeah, I'd save you money. You're not going to detect anything.
I did get an IR cut filter though. And
Yeah.
then I was so excited and I was so ready to use it. And then it proceeded to rain for a week straight. So,
Well,
and we've
right.
had crap seeing since then.
Yeah. Well, don't forget, whenever water vapor turns into liquid water, you get latent heat of vaporization released. So it'll be blazing away in the infrared.
Well, no, so I had an IR cut filter, not an IR pass filter.
Yeah, no, that's true. Okay,
Yeah.
so yeah,
So if
you're
anything, that
cutting
should have
off.
helped.
Yeah, if anything, it would have helped. Note to self: don't use your telescope in the rain.
Yeah. Yes. Well, that goes my plans for tonight.
Yeah.
Yeah, I live in Santa Barbara where it rains like 10 to 20 days a year, and all of them fall when I get new telescope equipment. Every single time.
That's what it's like to be an astronomer.
It's not
Although,
called the astrophotography forum isn't called clear nights for a reason. It's called
no, that's
cloudy
right.
nights.
That's right. Well, it's snowing here. I'm in Gloucester, Massachusetts, and it's snowing right now. So I won't be
Yeah,
observing
how is
tonight.
the blizzard? I heard it was gonna be really bad.
Yeah, it's pretty bad. It was pretty tame earlier on, but now we've got the several inches, and there's a fair bit of wind. But yeah, it's pretty outside, but I won't be observing tonight. That's for sure.
You know, they say that like after a storm, the seeing is the best. And I like saw that in many places. And then after a big rainstorm, I went out and tried to do some planetary observing, and it was garbage. And I feel like, is there some running joke in the astronomy community where you tell people that the best time to observe is right after rain, and then they go out and they're just disappointed?
Yeah. Yeah, it's a complete myth, right? Because of course, if you've got any precipitation, the energy in the atmosphere was probably high, and so that means turbulence, which is what
Turbulence, right?
seeing is bad turbulence, and so now you only get good seeing typically when you get good laminar flow of air, and that often is not associated with the after effects of bad weather.
I remember when you were observing, you were talking about laminar flow with, I think it was Alex or whoever it was. And I say it's really cool that these kinds of stuff impact your big, telescopes as well as just the consumer ones.
Oh yeah, it's actually nothing to do with the telescopes at all, really. It's to just do with the turbulence in the atmosphere.
Oh, but I mean, like, you
Yeah.
think for some reason I feel like there's some mystique, like, oh, we put these big telescopes, huge mirrors, many times larger than like a celestron, on top of like these high, super cold places, which I know does help with the weather a bit, but they're still subject to like the same effects at the end of the day. And it's
Oh
like,
yeah.
yeah,
Well, in fact, that's a large part of why we put telescopes on these places. So, for instance, the telescopes on top of Mauna Kea in Hawaii, one of the principal reasons is you get this beautiful laminar flow coming off the Pacific. So all the wind or air movement contours are very linear, very non-turbulent, and so you get very, very good seeing. And it's the same for all the telescopes in Chile. You get that laminar flow coming in off the South Pacific, and it's just wonderful for the seeing. Wonderful.
interesting. So where I usually go observing is like at the foot of a mountain, which is next to the ocean. So that sounds like could be the worst possible location, right? Because you'll have the flow from the water folding back over itself multiple times.
Yes, basically. Yeah.
Interesting.
Yeah.
That's good to
Sorry
know.
about that. Well, you live where you live.
Yeah. Reasons for leaving Santa Barbara. Seeing was bad.
Yeah.
The houses here are too expensive for the terrible seeing you get.
Well, there you go. That could be a good selling point for astrophotographers.
I want that on Zillow, like a freaking astronomical seeing category.
Most people are thinking, what the heck is this person doing?
uh,
Well, this wraps up another presentation for Astraveo, where we go from geek to chic by sharing our passion and excitement for all things scientific, especially astronomy and in the mysteries of the universe. If you enjoyed this video, please hit the like button, and in the comments below, please leave us your suggestions for future presentations. We'll get right on it. And don't forget, you can join us on our journey by subscribing and hitting that bell. He's Joseph, and I'm David, and together we're Astraveo. Thanks for watching.